Okay, so let's go over the concepts first for the weekend test, and then I'll go over a little bit of the math. All right, so I end up combining two different classes together. Some of you guys are taking calc-based physics, and some of you guys are taking algebra trig-based physics. So concepts are the same. Conceptually, they're the same. It's the same exact knowledge, except mathematically, calc-based physics is quite a bit more difficult. Okay, so I'll just, when I'm working on the easier problems, obviously that's for algebra and trig-based physics, and then eventually I'm just gonna phase you guys out. Those of you guys who are taking algebra trig-based physics towards the end, when we get into more complicated problems. Obviously you guys can just leave. All right, so more complicated problems are gonna be for those people who are taking calc-based physics. So that's, I'll mention it to you guys. All right, so I'll say, hey, this is where mathematically, once it gets a little bit more sophisticated, you can just get up and leave. Well, I'll give you a hint at that point. Okay, so that's how it's going. So as I'm lecturing, I get to chat up on the side. So if you have any questions, just write them down. In fact, let's do the following, just for the future. When you guys are studying for the test, just start your studies early on, actually. Don't wait till the last minute. A lot of these questions are understanding-based questions. Understanding is not something that you can cram. Okay, so whatever works here in physics, believe it or not, it's probably going to work in every single discipline that you're taking. Because in high school, you would memorize something. A lot of it was knowledge-based. This is a higher level learning, I'm going to say, which means that it requires some good understanding and critical problem solving skills, or something that you kind of develop along the way. And it's trial and error. It's trial and error. Don't be afraid to fail. All right, we got upgrades at the end of the semester. I mean, as long as you learn from your mistakes, you can always take the final test and ace it and get an A in physics. It's like a video game. You will kind of suck at it at first, and then the more you play it, the better you will become. That's how it is. That's how nature is, in essence. So don't be afraid to fail. Do your best and fail and learn from it. That's a good learning experience. All right. I did not succeed in everything that I did the first time around. And I mean, you learn from your mistakes. That's the best way to learn. Okay. These lectures that seem pretty good right now, these lectures took like a million years. I mean, it's just, I failed at it for year after year. Eventually you go, okay, so I figure out what works and what doesn't. And next thing you know, I have decent lectures at the art school. So it's okay to fail. Don't feel stupid. If you're feeling stupid, let me just tell you this, it's normal because you're doing physics. And no one feels smart when they're doing physics at that level, including myself. All right. So just understand that you will fail. Understand that you're not going to understand everything. Certain things will take a while to sink in. Okay. So with that in mind, there are upgrade tests. Okay. Do the upgrade test. Just make your mistakes. When I provide these feedback clips, video loops or whatever, just go back and listen to them. Learn from your mistakes, do the upgrades, get a passing grade, and then try to get better and better at it. And eventually, like I said, the final test, optional, you don't have to take it, but if it's better than your average test grade, it's going to replace your test grade from each and every single section. You can take the section separately. We'll talk about it more later. All right, so there's a safety net. Obviously, you can get less than a C, but at the same time, if you do it the right way, you don't need to get a C. You can get a B, you can get an A. So it's completely up to you, right? So I won't be curving. So that's not what's going to happen. You will literally have to earn the grade in this course. Plenty of tests, plenty of opportunities to succeed, and plenty of opportunities to fail, but you will get better at it. All right, just don't give up. Just keep at it. That's how it is. So that's my little spiel for it. All right, so the upgrade tests are available. Evidently, I made them available only on my computer, not on your computer. I'm getting some really good feedback from most of you guys. So I'm learning the Blackboard. I'm getting better at it. It's a new system for me. All right, so the upgrade tests are available. For test number 1, upgrade test 1 is available. All right, so I'm giving you guys like 3 days for that. Just take care of it. If you got less than 7 on any portion of the test, just make sure that you score 7 or better. Multiple choice section of the test, I'm giving you guys 2 attempts on that one. I'll keep the higher of the 2 grades, or if it's better than 7, obviously I'll give you a 7. For the math portion of the test, just go over the problem, the same problem. I'm going to give you the same problem. It's a formatting test. Just get the formatting right. That's the only thing I'm asking for. All right? Just get the formatting right. I'm going to give you the same problem this time around because I just want to make sure that you can do stuff in 3 steps. And so that it makes it easier to grade. Obviously, God knows how many students this semester. I'm at 3 different schools. And ideally, it's formatted so I can streamline the grading. Usually, I don't like spending more than 15 seconds to 30 seconds at most while I'm grading. So if it's formatted, I'll look at it, and I can just give you the rubric 1, 2, 3, whatever the numbers are, so you can see what the point deductions are from where, so you can figure that out yourself. So it makes my job easier. It makes your life easier. So you get the proper feedback. And the conceptual section of the test, once again, it's the only way you can do the conceptual section is watch the videos, the lecture videos. Okay. Some of you guys mistakenly think that it's online. Not a big deal. The standards are lower. Yes, it is online. It is a big deal. The standards are not lower. It's the exact same standards. I haven't changed my standards. I just make the courses better. Okay, I got better at doing this stuff online, obviously. Most of you guys think that you can Google stuff. It somehow is going to give you the information that I'm looking for on the test. Actually, it's not going to help. You can Google information, not understand it. If Google were smart enough, they would have taken you to my videos. So you have to watch the videos. It's not just watching the videos passively. You're not watching a movie or a show on TV. You have to study those videos. All right. So it's a lot longer. It's a lot more involved than what you think. Each and every single observation is a test question, obviously. And if it's an observation, if it's a test question, these are not yes or no test questions. You cannot answer them like that. You will have to answer it. While you're answering it, you have to provide an explanation. And for explanation, you have to provide a justification. Okay. So while we're doing our reviews, I'm just going to point out each and every one of them. Okay. The first one is I'm doing it. Let's focus on the knowledge, not the math. Okay. So, and then we'll introduce, I'm going to pick and choose a few problems and point out a few things. And then when the problems start to get a little bit more complicated, obviously at that point, it's for higher level physics. Okay. Let me just share a secret just for now. All right. There's no difference between calc-based physics and algebraic-based physics in terms of the test for the first couple of weeks. Okay. So the quality of the problems will be the same. All right. So hold on. Okay. So I see. Yeah. The difference of the explanation and the justification. She said, says a little bit confused. Yeah, you will be confused for a while, but eventually it's going to make sense. So we'll do more examples today. All right, so everything that we will do today is geared towards the test, so it should give you a really good idea of what I'm looking for. And then go over the main test questions, because the test questions come from the lectures, obviously. I'm not pulling something from somewhere else. All right, so let's, I was going to say something, then we'll come back if it's important. Okay, so we did a little bit of warm up. All right, so uniform acceleration is what you're going to test in essence. So you got the uniform acceleration, and the application of uniform acceleration is going to be free fall. Yeah, so this is being recorded.
This is the most complex and sophisticated machine ever made. In 6 minutes, it will be traveling at 17,500 miles an hour. In 8 minutes, the humans inside will no longer feel the pull of the Earth's gravity.
Okay, so there's something about the space shuttle mission was they had like 8 minutes. And within that 8 minutes, they had to travel 180 miles while reaching the final speed of 17,500 miles per hour. All right, so within that 8 minutes, just imagine that everything is on cruise control. Okay, no one is really piloting the space shuttle. Right, so now, in order to carry out something this complicated within the next 8 minutes and at these tremendous speeds, you have to make sure that the motion is predictable. Every single aspect of motion needs to be made predictable. So the question is, how did NASA make motion predictable? Again, I'm just going to turn the question to you guys. How do you make motion predictable? How does anybody make motion predictable? Okay, so we know something about predictable motion. The thing about predictable motion is it makes motion.
There is no danger, however, as the satellite's now expected to.
When it's predictable, it allows forecasting. Okay, so the satellite is coming out,
into quasi.
and they know exactly where it's going to land. That's predictable motion because they're able to forecast it. Not only they know when it's going to land, they also know where it's going to land. All right, so they know the when, they know the where, and they also know how fast it's going to land.
An uninhabited part of the Australian outback.
Now, this is 100% predictable. So it's on the landing site. So it's getting ready for him.
Do you Yahoo?
So not only is he ready for impact, so this is done. All right, so let's talk about impact. So another thing that I want you to notice is in physics, and what's true in physics is true in all sciences. Everything is related to everything else. All right, so notice that he's ready for impact because obviously they got all these pillows and everything else. And what will the pillows do? And most of you guys will say, well, because it absorbs impact better. That's not the explanation that I would be interested in because it shows no understanding what's going on. The reason why the pillows will help in this case is because it increases the impact and reduces the acceleration. All right, so acceleration is what kills you, what maims you, what breaks your bones. And the acceleration is inversely related to time. So larger the time, acceleration time is, smaller the acceleration becomes. So that's the reason why you want to increase the impact as much as possible. Okay, so that's a little bit of a review. So let's just keep doing a review right now. So measured distance over measured time is going to give you your average speed. Speed and direction combined is going to give you a velocity. If your velocity, measured velocity is changing in time, this is known as acceleration. Acceleration implies that you're speeding up or slowing down or changing direction. So how fast you speed up, slow down, or change direction is acceleration. So speeding speeding up is acceleration. Changing direction is acceleration. Combination of speed and direction, if they change, that's acceleration. So that's changing velocity. All right, so he's accelerating in the downward direction. Upon impact, the acceleration is going to change. So measured distance over measured time, average velocity. Measured distance, measured time, average velocity. Changing measured velocity in time. So changing measured velocity in time is your acceleration. That's your average acceleration. You measure the velocity here. You measure the velocity at a later time. If there's any change in velocity, this thing is accelerating in that direction. So that's average acceleration. You measure the acceleration at this point. You measure the acceleration at a later point. If there is any change in acceleration, that's called jerk. So that's your average jerk. All right, so changing acceleration in time is jerk. The example that we looked at is car collisions. So that's a collision lasting about 1/10 of a second. Engine compartment is crumpling. As it's crumpling, different portions of the engine is going to crumple at different rates. So what do we get? We end up getting jerk. So acceleration peaks at 150 Gs. So the question is this survivable? And Mythbusters used to just make this mistake time and time again. They were on TV for 10 years, and for 10 years, I saw the same thing. They were always looking at the top acceleration. Okay, guys, this top acceleration is not, this is your instantaneous maximum acceleration, peak acceleration. Is not what determines whether you live or die. It's the average acceleration. All right, so which means that you have to look at the average of the acceleration. When the acceleration is changing in time, just focus on the average acceleration. So when this is changing, when there's changing acceleration in time, you focus on the average acceleration. In this case, it's 25 Gs, it's survivable. All right, so instantaneous acceleration is changing in time, it gives you jerk. If there's jerk, what do we do? Use the average acceleration. Okay, because average acceleration is going to tell you whether something's survivable or not. So the average of the accelerations is what we are interested in. All right, so summary changing acceleration is time is called jerk. If there's jerk, use the average acceleration. Prime example is car collision. All right, so jerk in motion, the variable acceleration, whichever the way you want to call it, is unpredictable. It's chaotic motion. It's chaotic motion. All right, so you end up getting chaos. So how do you take something chaotic and turn it into something predictable? So the only thing you have to do is just get rid of jerk. Make sure that the acceleration is not changing in time. So which means that there's make jerk zero in essence. And how do you make jerk zero? By fixing acceleration to constant value. When the acceleration is fixed to a constant value, there's no change in acceleration. So when the acceleration is constant, three things about motion is going to become predictable. So the time becomes predictable, location becomes predictable at that time, and the speed becomes predictable at this time as well as at this location. All right, so that's it. The first formula gives you the location, x, at this time. So you know the time, you know the location. Second formula is going to tell you how fast it's moving at this time. So the final speed becomes predictable. The third formula tells you how fast it's moving at this location. So that's the third formula. So you know the location, you know the speed at that location. You know the time, you know the speed at that time. You know the time, you know the location at that time. So you know the location at this time, you know the speed at the same time, and you know the speed at the same location. So the motion is now 100% predictable. So when you fix the acceleration to a constant value, this thing is going to either speed up, slow down, or it's going to change direction at a constant rate. So motion becomes predictable when the acceleration made constant. So if you fix the acceleration, you know the location at this time. If it's NASA, if it's been 8 minutes, space shuttle should be 180 miles from the surface of the Earth. Once again, if you fix the time, you know the speed at that time. If it's been 8 minutes, it should be 17,500 miles. You know the location, you know the speed at that location. If it's located 180 miles away from the surface of the Earth, the speed should be 17,500 miles per hour. All right, so we looked at a few examples of predictable motion, NASA. Apollo 13, a real incident that took place, obviously, on the way to the moon. The oxygen tank exploded. So the question is, how do you bring the crew back home? There were two options on the table. Number one, stop and come back. How do you stop in space in the absence of friction? You have to go to the rocket field, just fire in the opposite direction of motion, come to a stop, and then keep firing to speed back up, and then come back home. That was one option. They decided not to use it. They figured that there's a better option. The better option that they decided was slingshot around the moon. So they figured out their free return trajectory first, and then put the rocket back onto the free return trajectory. So what that meant that near the moon, they had to slow down. So they have to accelerate in the opposite direction of motion for almost up to 10 seconds. And then in order to escape the moon's gravity, they have to accelerate in the direction of motion once again up to 10 seconds and remain on this trajectory all the way back. So they were able to come back. They were able to bring the crew back, more like it, by making the motion predictable and then keeping the rocket on this free return trajectory, and then things worked out. So while they're accelerating, the acceleration was constant. So the motion was predictable. Once again, they slow down at a constant rate, they speed up at a constant rate. The rest of the motion was at 0g, so they kept the acceleration at 0. That was also 100% predictable. So as a result, they were able to bring the crew back home. So NASA makes motion predictable by fixing the acceleration. So a couple of problems. A simple problem that we'll focus on right now. Simple yet important, because this is 100% related to the initial observation. So how does NASA make motion predictable? All right, so this is the main observation. All right, so how would you answer this question? Okay, so while you're answering it, here's what I'm looking for. Explain and justify. Explain and justify. That's an answer. So answer is composed of explanations and justifications. You can say yes or no if you say yes or no question. And then you have to explain it, and then you have to justify it. If it's not a yes or no question, the answer consists of an explanation and justification. All right, so how does NASA make motion predictable? The answer to that question is an explanation. They make acceleration constant. All right, so by making acceleration constant, they make motion predictable. So now you have to explain it. All right, so what becomes predictable in essence when you make motion, when the acceleration is fixed? Obviously, the time is going to become predictable because number one, it's going to take 8 minutes. So that's predictable. And within that 8 minutes, what else becomes predictable? The location becomes predictable. Now it's going to be 180 miles away. And then what else becomes predictable? The speed becomes predictable. Now it's going to be moving at 17,500 miles per hour. All right, that's it. So you can provide more explanation, obviously. So you have to eliminate jerk. What makes motion predictable is you have to eliminate jerk. You eliminate jerk by fixing the acceleration. And when the acceleration is fixed, the time becomes predictable, the location becomes predictable, and speed at that time at that location becomes predictable. That's it. So I provided a complete explanation with a little bit of justification. And the justification was related to jerking motion. That's it. All right, so now that we know the answer, now let's move on to the mathematical aspect of this lecture. Will the numbers really work out the way we expected? So let's fix the acceleration to a constant value. Let's check to see what happens. Right? I'll do something called brute force approach to it. I'll say, you know, orbital speed is 17,500 miles per hour. Okay, that's an orbital speed. You have to be at that speed so they're not coming down, crashing down. 180 miles is a reasonable distance. Atmosphere goes up about 52 miles, so this is 180 miles. So I don't know why they picked that distance, but there's got to be a good reason for it. So what's the amount of uniform acceleration I need? That's, you know, to get everyone up to the orbital speed within that distance. So obviously the next step is the metric units. All right, so, okay, so this is also a fast and quick demonstration of what I'm looking for on these tasks formatting. All right, so normally, high school, college, graduate school, I don't care where you do your physics or what discipline of science you're in. It doesn't matter what it is, metric units, and metric units. Okay, in engineering disciplines, they will let you do mixed conversions, and that's costly. The mistakes are costly. When I'm talking about mistakes being costly, I don't mean, oh, it costs you $50 extra. I'm talking about millions of dollars of mistakes per component. All right, it's gruesome. It's gruesome. In the United States, it just companies let you do that sort of stuff. And I know that at this school, I don't know who's majoring in engineering. Not too many of you guys, obviously. So that's fine. In sciences, strictly metric units. The only reason why I give you everything in British unit system, because I want you to have a real life experience with physics, because physics is not math. When you do the computations, the numbers have to make sense to you. The numbers in British unit system is the numbers that make sense to us. I want you to have a feel for what's going on. So it's not like high school physics. I don't care that you come up with a number and check it against the back of the book. That's not the way we do physics in real life. All right, so one of the things that you have to get used to is conversions. Forever and ever and ever, you cannot live life without doing conversions. If you're a scientist, you will have to do conversions forever. All right, convert the numbers from what you feel that you understand to the metric units, the scientific international units, and then boom, boom, boom. That's how it is. I want you to have a real life experience. You do your conversions in step number 1, not step number 3, step number 1. Get it out of the way. Get it out of the way. I'm not kidding. Get it out of the way, because what seems so easy right now, it's not as easy when you have all sorts of units that you end up pulling in. Because you got British unit system, and something could be given to you in liters, something could be given to you in ounces. You don't know. Just get it into the required unit in the first place. Because as soon as you start to put numbers into your computations, if something is off, something is going to be off. Everything is going to be out the door. Everything is going to be crashing, coming down. All right. So that's how it's going to be. So just get into the habit. Don't do anything else. You've got plenty of time. Do your conversions in step number 1 into the MKS unit system if it's motion. If it's not motion, once again, you have to scientific international unit system. You have to standard international unit system is where you're at. Do your conversions. All right, if something goes wrong here, if you don't do this stuff, your answer is going to be off. And some of you guys discovered it real fast. The next thing is for this week, because I'm just setting up the difficulty level of the math gradually. One of the nice things about listing everything with proper symbols and everything else, the proper symbols, and you got the standard formulas on the formula sheet, literally are the standard formulas. All right, these are literally the standard formulas. At the undergraduate level, we use these symbols. Some books may differ. I don't care. I'm already giving you what's considered standard in this course. Go to the formula sheet. Everything on the formula sheet is everything that you can use. Do not use any other symbols that you came up with or a different book to suggest that you should use. All right, so these are the symbols that we're going to be using. Nice thing about it is you look at the symbols and now find the formula that has those symbols. That's it. You got 3 formulas. You don't know which one to use. Boom, just use the formula for the symbols for this week only, because that decision-making process is going to get complicated in the future. Plus and minus. Just don't worry about the plus and minuses for now. Just go with the pluses until stated. Otherwise, that's a further discussion that we will have to have. All right, so formula looks like that. So what do? Isolate A. I'm not going to let you guys use any numbers when you do your algebra. You cannot use numbers. You cannot use numbers. I don't have time to go over your numbers. As soon as I see a number, I will put it aside. You will not get graded. Like I said, you're lucky that I got 15 seconds to 30 seconds per paper. That's all I got. I have 200 papers to grade. I usually have about an hour to do that. Yesterday, I spent 6-7 hours just writing back these, oh, this is missing, this is missing, this is missing, this is missing, this is. I don't do that. I don't have time for it. These are weekly tasks. Get used to it, all right? I explain when I do my problem. You explain when you do your problem. You will have to also start writing stuff. We will just introduce it gradually. Here, I'm picking up this equation because I said motion is predictable. I just want to know what the acceleration needs to be. So I'm moving at 17,500 miles per hour at a distance of 180 miles. All right, so if I have any zeros, I'll plug in the zeros because I want to simplify algebra. This is not math. All right, I do math while I'm coming up with these ideas, but my preference is I just want to do as little math as possible because I'm doing physics. I want to know what the answer is. All right, so I finish out my math. Okay, so this is complete. And now I can plug numbers into this. And notice that these are the numbers in metric units. It's going to give me an answer in terms of meters per second squared. So when I say do a conversion and show work, I mean do a conversion and show work, the details of the work, because I'm testing to see if you know how to do the conversion. Doing a conversion and showing work does not mean that you magically multiply 2 numbers and divide by a different number. That's not showing work, guys. That's not showing work. You're just putting down the numbers and you decided to multiply by a number and divide by a number without explaining why. It's not showing work. That's not what it means. Showing work means, hey, I'm going to multiply this with a conversion factor. And then when I'm multiplying with a conversion factor, this is what that means. Look, miles to meters, this is showing work. This is what I need to see. Here, once we get past the point of showing work, I'm moving the decimal to the left because I want to get a G load out of this for lecture purposes. If on the test I say show work, you get a show work. If it doesn't say show work, just go to the conversion and then just get to the final answer. So it would be about 10.5 Gs. All right, at 10.5 Gs, boom, you could be moving at 17,500 miles per hour within a distance of 180 miles. So just out of curiosity, the next thing I want to predict is the time, right? How long would it take? I mean, what am I looking at? Do I have enough time to maybe watch a football game while we are watching these people? I just want to plan my life, all right? So motion is predictable. Let me just figure out how much time it takes. I mean, how much time? While these guys are just traveling into space, what can I do with that time? So the best thing to do is just figure out the time. This formula and that formula will have time. So which one do you pick? Well, it doesn't matter. All right. Either way, you will get the same answer. You can pick the first one, you can pick the last one. Either way, you're going to get the same answer. I'll pick the second one because it's easier. Initial speed is 0. Isolate time from here. The numbers, just plug the numbers in. All right, so the final speed is 17,500 miles per hour. That's not what we use, obviously. We got to use the number in terms of the metric units. Acceleration is going to be 10.5 Gs. We don't use that. We use the one in metric units. So it's going to give you a time. So it's going to be 1 minute and 14 seconds. Yeah. So you fix the acceleration. It'll take 1 minute and 14 seconds. Within 1 minute and 14 seconds, space shuttle is going to be traveling at 17,500 miles per hour. And it's going to be located 180 miles from the surface of the Earth. Okay, we're good. So things worked out. Now the reality check. It doesn't take 1 minute and 14 seconds. Reality takes about 6 minutes plus 2 added minutes to get things just situated just right that they're moving in the same, right direction. All right, so there's 6 minutes of acceleration that they use, and everything is done within 8 minutes. Why? All of a sudden, the thing to focus on is this number. Is it, all of a sudden you're thinking, is it possible that these people cannot handle 10.5 Gs for 1 minute and 14 seconds? Well, you know from pilot centrifuge studies that the pilots can handle between 75 Gs up to 3 minutes. Worst case scenario, you may pass out within that time period, but it's not going to be deadly. So you'll be sleeping for a while. That's what it means. So it's not that it's going to kill anyone. It's just the 10.5 Gs on takeoff is going to, it would shake the space shuttle into pieces. It would break apart because there's just too much air pressure, doesn't there? So what they do instead is they use multiple stage rocketry. The first stage acceleration is fixed at 3 or 4 Gs, but the number up to 2 minutes or 3 minutes. As the atmosphere starts to get thinner, they throttle up to 5 or 6 and then stay there for a while. And then by using variable stage rocketry at each and every single stage, they use a constant acceleration. And they make motion predictable that way. So it's slightly more complicated and involved than our company. Okay, so copy those down. And then on Fridays, just email me that stuff. Okay, when you have questions, just write them down and then email me your questions. All right, so I can just incorporate those questions into these recitation sessions as well. All right, so whatever the questions you may have. All right, we can always go over. All right, so following objects, let's discuss that. So the following objects, because when dropped, they will go to something else. And thrown up against gravity, they will slow down, right? So the next question is, well, now that we know the following objects accelerate, the question is, will they all accelerate at the same rate? Or let's put a little bit of common sense into it. Will that rate of acceleration vary depending upon the weight? Because your common sense will explain the understanding of reality is heavy objects, you kind of expect them to fall faster, right? But when you do the experiment or a demonstration in a complete vacuum, in an airless environment, and when you actually carry it out, and you guys have seen the video of it, they've done it at the surface of the moon, I was going to say Mars. When dropped, the hammer and the feather end up falling at the same rate, right? So, which means that the weight doesn't matter. Okay, so in a vacuum, Galileo said when he came up with this concept 400 years ago, all objects will fall at the same rate. So, falling at the same rate means everything is going to speed up at the same rate. And the rate at which things speed up is roughly about 10 meters per second squared. Actual number is 9.8. So that's something that you will get to verify. That's going to be your lab number 2. I'm going to make it available this week. I'll make it available next week, and I'm going to give you guys 2 weeks on it. That's a fun little lab that you will get to do at home. So it's 9.8 more or less. So we say 10 approximately. We end up using 10 because it makes discussions easier or quick computations easier. All right. So freefall. In freefall, the acceleration is fixed to a constant value, so G is fixed. So G is the acceleration due to gravity. We end up using the letter Y, which tells us that the motion is occurring along the vertical direction. So this is the Y direction. And so these are the constant motion formulas. Okay, so motion is on the Y direction. You know the time, you know the vertical location at that time. You know the time, you know how fast it's moving at that time, how fast the object is falling at that time, you could say that. And if you know the location, the vertical distance, you know exactly how fast the object is moving or falling at that time. So that's the meaning of it. So let's focus on the concept first. So drop a ball, throw a ball down, and then throw a ball up. All right, so it's all of them are free fall. All right, so the ball is falling under the influence of gravity. Throw a ball in the downward direction, throw a ball in the opposite direction. Which one has the largest acceleration? The ball thrown up or the downward direction? All right, so no, forget that. Which ball has the largest acceleration? So throw a ball in the downward direction, you drop a ball. All right, so throw the ball in the downward direction and drop a ball. Which one has the largest acceleration? The second scenario is you can throw the ball in the upward direction and in the downward direction, up, down, identical speeds. Okay, so both balls at some point will land, hit the ground. So the question is, which one is going to have a larger impact speed? Which one is going to have a larger final speed? The ball thrown up at some point will slow down to a stop. At the peak of its trajectory, it's going to have a 0 speed, so it's not going to be moving. At the peak of trajectory, it stops moving. That's what it means. So what's the acceleration of the ball when it reaches the peak of its motion? All right, the lastly, you're throwing the ball, you're in contact with the ball. What's the acceleration of the ball while you're touching the ball? So let's ignore that one. So the 3 questions. All right, so drop the ball. Motion is going to be under the influence of gravity, so there's going to be an acceleration. 1 second later, the ball is here. 2 seconds later, the ball is going to be here. The ball is falling under the influence of gravity, so this ball is going to go from 0 to 10 within the next second. Okay, 10 meters per second squared means the acceleration is 10 meters per second each and every single second. So, which means that the object is gaining speed at a constant rate of 10 meters per second each and every single second. So it goes from 0 to 10 within the first second. and 10 to 20 within the next second. That's it. So acceleration is 10, acceleration is 10. What happens when you throw a ball in the downward direction? So imagine that the initial speed is 20 meters per second. That's like 45 miles per hour. So gravity takes over. So gravity is going to make it go even faster with the next second. So it should be moving at 10 meters per second faster during the next second. So it should be 30 meters per second. All right, once again, when you drop it, it goes from 0 to 10 within the next second. Acceleration is 10. When you throw it, it goes from 20 to 30 within the next second. Acceleration is still 10. Okay, so which one accelerates more? Both the same. All right, so both of them will speed up at the same rate. Both of them are going to accelerate at the same rate. Okay, so both of them are speeding up at the same rate. Which one is moving faster? This one is moving faster. Which one is accelerating faster? Neither. Okay, so don't get the terms confused. They have the same acceleration, except this one is moving faster. Okay, so the only difference is the initial speed. No initial speed here, there's an initial speed here. 1 second later, whatever the initial speed is, it's going to be moving 10 meters per second faster. All right, so the next scenario, throw the ball up and a second ball down with identical speeds. Let's follow this for 1 second. Gravity takes over. So it's going to be moving 10 meters per second faster than the next second. So it's going to be 30. I'll place the ground here. Okay, now let's follow this one. This one is going up against gravity, which means that it's going to slow down, right? So it's going to go from 20 to 10 and 10 to 0, right? All right, and so every single second, the speed is going to be 10 meters per second slower. Okay, stops and then turns around. Now that's what goes up, comes back down. So now it's going to be moving 10 meters per second and 10 meters per second faster and 10 meters per second faster. So it's also going to hit the ground at 30 meters per second. So identical final speeds when they're identical initial speeds. This takes 1 second. This is going to take 5 seconds. That's the only difference. All right, so the next question is, at the peak of its trajectory, this ball stops. What's the acceleration? Common sense will say 0. Speed is 0, not the acceleration, guys. All right, so your common sense is wrong. Once again, your common sense will say 0. Hey, it's stopped. It's not a bus stop. It's not like you come to a stop and stay there. That's just part of continuous motion. My question is it moving before it stops? Yeah, if one of the velocities is not 0, it's always accelerating. So is it moving like a second before it stops? Yeah, it's moving. Half a second before it stops? Of course it's moving. A fraction of a second before it stops? Yeah, it is moving. A trillionth of a second before it stops? Is it moving? Yeah. Zillionth of a second before it stops? Is it moving? Yeah. So if it's moving before and after it stops, it's always accelerating. Acceleration is how fast the velocity changes in time, right? You got two velocity values. One of them is not 0, which means acceleration. So it is accelerating. What do you think that acceleration is? Well, you can figure that out. 1 second before, it's at 10. So within 1 single second, it goes from 10 to 0. So acceleration is 10. Within the next second, it goes from 0 to 10. So the acceleration is still 10. So it's the same as gravity. Acceleration due to gravity. So once the ball leaves your hand, you are always accelerating. And then the acceleration is the same as acceleration due to gravity. It's free fall. All right, now the mind twisters. All right, so according to this Darwin Awards, the attorney in Toronto, Canada, he wanted to demonstrate the strength of the windows in his office building. And what better way to do it than just running towards it and throwing your body at it. So he puts his shoulder, the window gives, plunges these daft 24 floors, 250 feet. So the conclusion is falling for a distance of 250 feet and hitting ground is not surviving. That distance is not, fall through that distance is not surviving. Regardless of your nationality, it's not surviving. All right, so the question is, how about a cat? The cats are said to have 9 lives. Can a cat survive this? That becomes a question. Well, if we're going to be dropping a cat, we might as well just go to one of the tallest buildings in the United States. The one that we got there in Chicago, and formerly known as the Sears Tower. The current name is Willis Tower or Big Willie. It happens to be about 1,450 feet tall, and then just take a cat and then drop the cat. All right, so here's the bird eye view. What's going on with the cat? All right, guys. Originally, when I was preparing these lectures, that was 20 plus years ago, we didn't have the luxury of having access to all these amazing sound effects that you could buy or download. So I had to get the sound effects out of my cat. And she was not very cooperative, obviously, so I had to squeeze her really tight. At the time, I had a Maine Coon. She was more like a dog than a cat, so she thought that I was roughhousing, so she was purring at first. And then she got uncomfortable, and then she thought that we were still playing, so she wasn't cooperating. Eventually, I squeezed her so tight that I was able to get the sound effects that I was looking for, except I got scratched pretty badly. So the question is, will the cat survive or splat? can indicate that this is not survivable, despite the fact that the cats will do just fine. All right, so the longer the distance of fall is, anything over 70 feet, it's much more survivable for a cat than anything under 70 feet, because it's what happens. So falling from the top of the stairs tower, most cats will do just fine. So the question is why? There are two reasons for it. The secondary reason is the one that we will focus on this week. The secondary reason is is related to impact and how you go about surviving impact. The thing about cats is they tend to be so much better at absorbing impact. The absorbing impact means that they are better at increasing the impact time and reducing the acceleration. Okay, that's what it means. When somebody says absorbing impact, that's just poetry at that point. It's meaningless words. You got to feel for it, and it doesn't mean anything in physics. Absorbing impact just means that requires a translation, which means that the acceleration becomes survivable. The reason why the acceleration becomes survivable because somehow something increases impact. They got extra muscles in their hind legs as well as in their shoulders. All right, so they're able to increase the impact time, and they're able to reduce the acceleration as a result. All right, so that's the secondary reason why. So that's a test question. That's a test question, conceptual test question. Why is it that the cats tend to do better in longer distance falls? Because they got extra muscles. They're able to increase the impact time and they're able to reduce the acceleration. And acceleration is what kills and what maims you. I provide an explanation. I also provide a justification. So that's how you answer that question. Wrong way to answer this question is, oh, because they're able to absorb impact so much better. Guys, that's not a physics explanation. That's a movie explanation. That's a commercial TV documentary explanation. You wouldn't see those kind of explanations on PBS or BBC. No scientist would use an explanation like that. That's not a physics explanation. Or absorbs impacts on it. What does it mean? That doesn't mean anything. All right. You have to just dig into it and figure out the concept that we're focusing on. The concept is surviving impact. And the surviving impact is surviving acceleration in this sense. Right? It depends. Is the acceleration survivable? It depends on the impact time. Larger impact time, smaller acceleration, that's what becomes survivable. Another monk twister that's obviously is going to be on the test this week. Regarding this guy, finding himself in a falling elevator. He's got a broken neck, paralyzed from neck down, got an attorney, suing the elevator company for $100 million to recover damages. Attorney comes to you, and then he wants you to animate a 20-second animation portraying what happened to this guy inside the elevator. That's it. If they win, you get 10% of the earnings. If not, it's a free animation. In essence, that's what's going on. All right, so the first thing you do before the animation is called a storyboard, and then you do an advanced storyboard, and then from the advanced storyboard, you do the animation. So this is the advanced storyboard step. Everything that you're about to see is everything that most of you guys were thinking. There's nothing disagreeable about the storyboard. This says, if I were to talk in the beginning of the semester, each and every one of you guys for 2 minutes, and ask you out your theory, and most of you guys will come up with something like this. The guy walks in, of course, it's an animation. The guy's happy, he's got a job. And then his tongue is sticking out, the spit is goes up. Right, either the first or the second hit, he's gonna break his neck. All right, so that's majority opinion would agree with this animation. Except there's a catch. That's not at all what happens. Contrary to what you think, what your common sense dictates. What happens is this guy, he's gonna remain on the floor. He's not gonna go up and hit the ceiling. He's gonna remain on the floor. And there's a safety system that's going to catch the elevator and bring the elevator to stop jumping. Why? Now it doesn't make sense. No, it should make perfect sense. Why would he stay on the floor? The reason why he's going to stay on the floor at all times is because of what this guy has is free fall at that point. What happens in free fall? Everything falls at the same rate in free fall. Everything. Elevator, the person inside, the feather inside the elevator. The atmosphere inside the elevator, the atoms and molecules making up that, everything falls at the same rate. Nothing is special. Everything, yeah, but I don't get it, man. I don't get it, man. It's only the when only the gravity is the only force acting on it, everything falls at the same. How about air friction? What air friction, guys? What air friction? What are you talking about? Do you know how heavy the elevator is? It's like a ton. Distance falling, what is it, 500 feet, 1,000 feet? Do you think that the air is going to have any effect on that elevator? No. It says the amount of air friction, the effect of air friction on that elevator is negligible. You're inside the elevator, you're shielded from the effects of air friction. So you're falling at the rate of gravitational acceleration. So is the elevator. So you're on the floor. That's it. You will remain on the floor of that elevator, all the way down to the safety system. Yeah, but you know the safety system kicks in, and that's the reason why the guy's next snaps. Are you kidding? What I just described is exactly identical to giant drop. If you go to Six Flags, what I just described is 100% identical to the Tower of Terror. Right? there's an elevator, you're inside of it, they just let it go in a free fall, in essence. And there's a safety system that kicks in. How many people have broken necks at the end? Not a single one of them. If you break a neck, no one is going to be using that thing. It's a safe free fall. Elevators are designed. If something goes wrong, it'll catch the elevator. Safety system will kick in at some point. It'll bring the elevator to stop jumping. Yeah, you got a person with a broken neck inside the elevator. Despite the safety system. This guy doesn't go up and hit the ceiling. There's no such thing. Safety system is not designed to break somebody's neck. It's called safety system. So in case something goes wrong, you're safe. So the question is, how did this person break his neck? The next question is this scenario even remotely possible? It's possible that I just came up with it in order to make the lecture interesting. I came up with it in order to make it interesting, but at the same time, I knew that it could happen. If it did, I also knew that you could have broken bones. There's no question about it.
After their
And then it did happen.
elevator plunged 40 stories. That story tops tonight's news briefs. Miraculously, the women suffered only minor injuries. One woman broke her ankle, the other broke her leg. After traveling down 6 floors, the elevator suddenly broke loose and began its free fall descent.
Yeah, so you got 2 people inside. Elevator goes in a free fall. Safety system kicks in. Both of them got broken bones. You can break a leg, you can break an arm, you can break your back, you can break your neck, despite the safety system. All right, so that's the reason why when you're inside a giant drop, a tower of terror, they strap you in because obviously they don't want you to be moving around and you are in a seated position on purpose. You can break bones otherwise. So the question is how that happens. Okay, so speed expressed in terms of direction becomes velocity. Acceleration is how fast your measured velocity changes in time. So how fast you speed up, slow down, or how fast the velocity changes in time, or how fast the direction changes in time. Okay, they all mean the same thing. Change in acceleration in time is called jerk. The motion itself is called jerk motion. Motion becomes predictable when you eliminate jerk. So 3 things about this motion will become predictable. The time is going to become predictable. Location becomes predictable, and the speed at that location becomes predictable. 3 things. All right, so the following objects do accelerate. Experimental proof that the following objects accelerate is one drop, they will go from 0 to something else. Thrown up against gravity, they will slow down. Acceleration is going to be constant. The weight doesn't matter. All objects will fall at the same rate, regardless of their weights. The value for acceleration is roughly about 10. The actual number is 9.8. When an object is dropped from rest, it's going to be moving roughly about 10 meters per second within the next second, within the first second, and 20 meters per second during the next second. All right, so which one accelerates rest? The one which you drop from rest or the other one falling with an initial speed? They will have the same acceleration. The one drop from rest is going to go from 0 to 10 within the next second. And the other one falling in the downward direction is going to have an initial speed. And it's going to be moving 10 meters per second faster than the initial speed in the next second. The acceleration of an object falling in the opposite direction at the peak of its trajectory is still going to be 10, despite the fact that the speed is 0. Because it's still going to be moving before and after it stops. So acceleration is how fast you slow down, speed up, or change direction. So if something is moving before it stops and after it stops, it's always accelerating. So what do we have? We got a hammer and a feather. Drop from the same height on the moon's surface. Go air friction to speed up, so which means that gravity is going to force. If that's the case, they will both accelerate at the same rate. Okay. So which object, the hammer or the feather, drop from the same height? Is a larger acceleration, so both of them will have the same acceleration. So the accelerations will be identical. Okay. In terms of problems. Okay, so a couple of things to focus on. Okay, so you got uniform motion, you got free fall. Okay, free fall is the same as uniform motion. The formulas are identical, except the symbols are different. Okay, so formulas involving x is the motion along the x direction, horizontal motion. Formulas involving the letter y, vertical motion is free fall. My advice to you guys is pick and choose at least one problem from each section and just do it on your own and check it against the video. Okay, because test question is going to be similar to those. Just practice before doing a test. Make sure that you know how to get the formatting. All right, so if I can make a suggestion, problem number 8 is good. Okay, so problem 8 is kind of involved. We'll just take a look at that. And then from here, my recommendation is problem number 20. Okay, so problem number 20 has free fall. It's got impact, so it's got a bunch of stuff. And problem number 20 is similar to problem number 18. So I would do number 20 for that. Okay, so those are the 2 problems that I'm going to focus on just right now. Okay, so problem number 8, I kind of like problem number 8 because it's almost cubed, so it's not that complicated. And in terms of the complexity, it's got the proper level of complexity. It's a good test question. It shouldn't take you more than 10, 15 minutes to solve it. It'll give you enough time to actually convert it to PDF and then attach it. It's going to give you plenty of time, in essence. All right, so problem number 8. And let me just make sure. Okay, so we are right now. Okay, so once again, problem number 8. So make sure that you understand that these are formulas that you will get to use. Because it's uniform motion, predictable motion. So you got 300 feet to take a fighter jet from 0 to 140 miles per hour. So what's the required acceleration? Okay, once again, the convergence. Use the convergence sheet for that one. All right, so feet to meters, miles per hour to meters per second. All right, so we got our numbers in terms of the correct units. Okay, so now we'll make a decision based upon the symbols. So we got no time, time is not given. This is the only formula that does not have time in it, so boom, solve that formula. Initial speed is 0, so that makes life easier. Solve for A. And then plug the numbers in. All right, so it's move the decimal to the left, so it's going to be 2 G's of acceleration. So acceleration is constant, it's manageable. If something goes wrong, you're still in charge. Okay. So next question is, how long would it take for it to clear the deck? So that's the other information that we want. Okay, so you got 2 formulas. You're going to have T in it. All right, so this has T in it, so it's this one. All right, and boom, boom, boom. So use initial speed, 0 still. Solve for T. I decided to use the second formula because it's easier. And plug the numbers in. It's about 3/7. Okay, so unlike last week, this week, you will also have the multiple choice math portion. Those of you guys who are taking algebra trig based, you will have 5. Those of you guys who are taking calc-based physics, you will have 10 questions. All right, in either case, you got 15 minutes. All right, so which means that you're going to be forced to solve problems like this, except you either have 5 minutes or 10 minutes. And problems are straightforward. You don't have to do conversions on multiple choice test questions. Everything is usually given to you in terms of SI units. So just want to make sure that you guys know how to pick these formulas. Okay, so that's an example. This, if you did this problem while you're studying for the test or something similar to it, you'd be more than ready for this test. This is what I'm talking about. So it's a 5 second. So it's a 5 second. So it says it's a double jump. Obviously, it jumps. So the question is this a survival jump? Okay, so that's what we're analyzing. So you got 5 seconds. Within 5 seconds, you'll go from 0 to God knows what. So that's what we're trying to figure out. And then we will have to assess whether or not it's survival. So 4 symbols. The only formula that makes sense to use is the second one. Initial speed is 0. So G is going to be 10, time is going to be 5. So it's going to give you 50 meters per second. And then in order to make sense out of these numbers, we do a conversion to miles per hour. So that's 112 miles per hour. So the question is, can you survive hitting water at 112 miles per hour? Okay, so your common sense, once again, is going to scream no. You will say no. Common sense will say no. No, because immediately, it's kind of funny. People always come up with the same argument. Oh, you know, it's like getting hit by a train at 112 miles per hour. Hit water at 112. It's like you're hitting concrete, man. Yeah, so the question is, can you survive getting hit by a train at 112 miles per hour? The answer is no. How about hitting water at 112? Say no again. How about hitting train at 100? Getting hit by a train at 112? The answer is no. How about hitting water at 112? The answer is still no. And then I asked why, because it feels like you're hitting concrete. I get an answer like that. It's so cute. The difference is water gives, guys. Train does not. All right. The difference is water gives, the train does not. When you hit water, it may feel like you're hitting concrete, but the water gives. When was the last time you felt so thirsty that you tried to drink a train now? All right. You can do this before you hit water. Try to do the same thing in front of a train. It's not going to make that much of a difference, right, when a train is. All right, when you hit water, water gives you an impact time. The worst case scenario, when you end up landing on your side, on your back, it's about 1/10 of a second. You will feel it. How do I know that you will feel it? Because people say it feels like hitting concrete. It's got a feel to it. If you're feeling it, there's a large enough impact time for the pain to register. That's usually a large enough impact time that makes it also survivable, because when you get hit by a train, there won't be a large enough impact time for the pain to register. What does it feel like to be hit by a train? It feels like nothing. There's not going to be any pain associated with it. It's going to be a permanent out-of-body experience, but there's no pain involved. Hitting water is going to involve quite a bit of pain in the worst case scenario. So you end up landing on your side, on your back. Let's take a look at the worst case scenario. Let's check to see if it is survivable. So I'll give it a 1/10 of an impact time for the pain to register. So you hit the water at 112 miles per hour. So that's your final speed in free fall. So that becomes your initial speed and impact. So the impact is going to last. This is an estimated impact time, 10th of a second. I'm also making the assumption, and the quality of your solution is going to depend on the quality of the assumptions, and there's simplification in these assumptions. Somehow magically you go from this speed to 0 within 10th of a second. That's not true in reality. And so what's the acceleration? So I'm looking at the worst of the worst case scenario, landing on your side and coming to a stop in 10th of a second. Final speed is 0. Boom. This is your initial impact speed. That's your final speed in free fall. Here's your estimated impact time. Your final speed in free fall is 50. Estimated impact time is going to 10th of a second. Boom. It's going to give you 500 meters per second squared. Means decimal to the left. You got 50 Gs. Is that survivable? Okay, so when I ask a question on the test like that, these are not yes or no questions, and these are not one single word answers either. You don't say survivable and not survivable. That's not a guesswork. Okay, once again, just like in the conceptual section of the test, you have to explain and justify. 50 Gs for a 10th of a second, would that be survivable? You answer that question, yes, of course it is survivable, because for a fraction of a second, we know you can survive up to 100 times 40 Gs, all right? But then again, over 25 Gs, you expect to break bones, so it should be survivable with broken bones, basically. That's what you would expect. It's a perfect justification and explanation. I gave you the numbers. I based it upon these things.
I have no reservations other than my own fear. And use your frequent fly.
So what's the extent of the damage on the sky?
Make a reservation
And that fracturing is back.
on the born to lose plane. And
He did survive. He passed out. Got a fractured back.
use your frequent
The odd part of it is,
flyer mind. He still thinks it was a good idea.
the weird part of the entire thing is he turns his body. He's doing fine. He starts to turn his body for whatever, I don't know what he's thinking. He's not thinking too much. Obviously, thinking is not this guy's forte from based upon everything that I've seen. And then another thing that he does for whatever reason, he gets his body parallel to the ground. And he's thinking, oh, I'm just going to disperse the impact force. And then as a result, he reduces the impact time quite a bit to an extent that he fractures his back. That's what happened to him. All right. A lot of people jump from bridges. Obviously, if you see someone jump like that, you're thinking, oh, the person's committing suicide. You never think, oh, this guy's testing to see if something like this is survivable. I mean, this is insanity. This is beyond dumb, I gotta tell you. So, and he experiences about 50 Gs, large enough to break his back, and that was the end of it. He also ended up passing out. The interesting thing is, though, if he just did not turn his body and then hit the water in this position, he would have experienced the best case scenario, which is what? Would have been a large enough impact time. You're going down, head down first, or feet down first. Impact time would have been about 1 G, that would have been about 5 Gs, all right? And that would have made a believer out of him in a sense that, oh, now it's a miracle that I survived. All right? He would have survived this without any broken bones. It's not a miracle, it's just an angle of impact on the certain. He would have been fine. All right? He would have experienced later 5 Gs, that's it. That would have been fine. Now, hitting concrete from that distance, 50 Gs, is about 5,000 Gs upon impact. Concrete doesn't give, so your body has to. So you get your impact time from your bones from that distance and from your body. All right, so that would be dead upon impact. There would be no pain associated with that one. All right, so why then a lot of people who jump from bridges die if it's so survivable? Well, the reason why they die is because of what happened to this guy. Number one, it's the worst case scenario, 40, 50 Gs, you will pass out. Definitely you have broken bones all over the place. You won't be able to swim. You go in and out of consciousness. No one sees you fall. Obviously, you're going to end up drowning at some point. All right, that's what happens to a lot of people. It's not impact. They don't die of impact. They don't die upon impact. They do survive the initial impact. Most of them do. So that's a horrible way to go. It's a horrible, horrible way to go. All right, so that's an illustration of everything that I wanted to talk about. All right, so these are my recommendations. Just go over these problems. We'll find something similar, all right, for the upcoming test. All right, so what else do I need to say? All right, so these are the example problems that we went over, and that's pretty much it. Okay, we're done. All right, does anybody have a question? Questions, concerns? Do you want me to explain anything more, clarify things more? Let's talk about Freefall. Questions for the conceptual portion of the test. All right, so for the conceptual of the test is anything and everything related to Freefall. Remember the ball thrown up, down. You throw one ball in the down direction, drop the other ball. And always the question is which ball has a larger acceleration? Hold on. All right, so that segment, every single thing that we covered in that segment is a test question. All right, so just, all right, so make sure that you go over those. All right, so I'm just gonna edit this. I'm gonna put this up online. So obviously, if you guys wanna go back and review it, that's fine. We'll just do so. All right, and the cat, the secondary reason as to why a cat survives, just focus on that one as well. The reason is because, I mean, regardless of the distances, the cats will do fine, except anything less than 70 feet, injuries tend to be more severe. Over 70 feet, they tend to be less severe if there are any injuries at all. And once again, surviving impact is surviving acceleration, and what makes acceleration survivable is always the large enough impact time, right? So larger the impact time is, the more survivable it becomes.